Hi, my name is Sydney, and today I'm going to be presenting my PowerPoint for our science investigation project. My project was on the effects of a ramp's angle on the distance a toy car can travel. So my research question was looking into the effects of a ramp's angle on the distance traveled by a toy car, and we're trying to see if there is a significant difference based on the ramp's angle being higher or lower affecting the distance traveled by the toy car. So here is some background information to help make sense of the experiment a little bit more. So the first thing we're going to be talking about is potential energy. So potential energy is referring to energy that an object can store based on its relative height to a reference position. So let's say I had a rock suspended from the air like 10 feet in the air. That rock is going to have a lot more potential energy because it's suspended in the air than a rock would on the ground. It's more likely to move eventually or have more force when it moves. So an object may have the capacity for doing work because of its position, because of this potential energy that it's like building. And a good example of potential energy can be used with like a bow and arrow. So if you look to the picture on the left, you see a man drawing back a bow and arrow. So the string that he's pulling back on, he's creating a lot of potential energy in that string. And once the string is released, the potential energy is going to turn into kinetic energy, which is then going to propel the arrow forward. So the next thing we're going to be talking about is kinetic energy. Kinetic energy is energy in motion or motion energy. So this is when an object is moving, pretty much. So if work is done on an object by applying a force, the object will gain kinetic energy and accelerate. I think the picture to the right does a really good job of illustrating that. And the relationship between potential energy and kinetic energy. So if you see like on the left of the picture, there's a weight being suspended by a pulley in the air, and because this weight is up in the air, it has a lot of potential energy. And then when the string is cut and the weight falls, that potential energy turns into kinetic energy, which allows for it to fall to the ground. And because it's on the ground now, it no longer has as much potential energy as it did in the air. So yeah. And I also stole that picture from the textbooks. Oh yeah, they have a lot of good images in there. So the next thing I'll be talking about is an inclined ramp. So an inclined ramp is a simple machine, and it can help change the direction of a force or lessen the force on the person trying to move an object up or down the ramp. So ramps help move objects like up and down a lot easier and like more gradually. Um, and yeah, we're doing an experiment with some ramps today. So my hypothesis is that I think that the inclination of the ramp, the higher it is, the farther the distance the toy car will travel, because the higher the ramp is, the more potential energy the car will have, and that potential energy will convert to kinetic energy when the car is released down the ramp, and more kinetic energy means more movement. So I think that's going to mean it travels a farther distance. So here are some of my variables. Independent variables are the thing that we are changing in the experiment. So for this experiment, our independent variable is the inclination of the ramp. Dependent variables are the things that change based on the independent variable, and that's what we measure. Um, Sorry about that. uh, Dependent variables in this experiment are going to be the distance traveled by the toy car down the ramp. And lastly, our controlled variables. Those are things that we are keeping the same across all of these trials that we're conducting. And some of my controlled variables is the car that we're using. We use the same car for all the trials, and also the surface that the car is rolling down. Because if I change the surface that the toy car rolled down, there might be some different kinds of friction, and that would just really skew our data. So I kept the surface the same for all the trials. Here are some of the materials I used. So a black toy car, a ramp with a protractor, note card, lots of meter sticks, and some tape. So here's my methodology. So to set up the experiment, in this picture to the right, you can see the ramp I used, and there's like a protractor thing attached to it to help you measure the angle that the ramp is sitting at. And then at the end of the ramp, unfortunately, it didn't like go flush with the counter or whatever it was sitting on. So I attached a note card to the edge with tape, so it would hopefully provide a more gradual drop off. And this would also keep the car on the track that I created for it. So after this, I picked 3 different angle measurements for the cars to go down. So we have 8 degrees, 10 degrees, and 12 degrees. And then for like the 8-degree angle, there were 10 trials conducted for that one, and then same for the 10-degree and the 12-degree. So 30 trials were conducted all in total. And lastly, when releasing the toy car, I put the back wheels off the edge of the ramp, as you can see in the picture, kinda, I hope. And ever so slightly, you just like lift it up, and then it'll go down the ramp. And I did this to ensure that there would be kind of this continuity of where the car was released, so that wouldn't skew the data at all. Because if I started the car at different points all throughout all the trials, that's obviously gonna have an impact on how far the car goes and everything like that. So here are some pictures of me conducting the experiment. The big one on the right, that's me about to push the car down the ramp. I think you can kind of see all the meter sticks and stuff, like creating the track. The picture on the top left is a better angle of the ramp setup and everything. I think you can see the protractor a little bit better on that. And then the picture on the bottom left is the picture on the last slide, just to show you where I'm letting go of the toy car every time. Shout out Dr. Wilson for taking these pictures for me. So here's my data table. So you can see that there's the 3 different angles, 8 degrees, 10 degrees, 12 degrees, and then 10 trials conducted for each, and then all of the measurements or the distance traveled by the car. I will say at the beginning it was kind of freaking me out that the numbers were all over the place. But a little bit later on, we're going to make a little bit more sense of this data. So here's the data analysis. So for group 1, the 8-degree angle, the minimum was 237 centimeters, while the maximum was 309 centimeters. And our average was 272.5. So the average is adding all of these data points up from group 1 and dividing them by 10. And then that's our average distance traveled from an 8-degree angle incline, so 272.5 centimeters. And then group 2 in the middle, that's the 8-degree angle. So the minimum was 285 centimeters. Our maximum is 333 centimeters, and bringing our average to 307.1. And then for group 3, that is the 12-degree angle. So our minimum is 287.5 centimeters, with our maximum at 200. That's supposed to say 300. We're fixing that later. 367 centimeters with an average of 343.4 centimeters. So even looking at this, you can tell that there is a very obvious change based on the angle incline. So the lowest incline, 8 degrees, that has the lowest average, so the lowest distance traveled, while the group 3 has the highest distance traveled, and that is also the highest incline. So that's pretty interesting. Here is my graph. I think my little bubble is covering it, but the y-axis is measured in centimeters, by the way. So here we have our 3 groups being graphed with all of these data points. And yeah, this is kind of confusing to look at. I won't lie. But the red line is the 12-degree angle incline. The green line is 10 degrees, or no, that's the green line is 8 degrees. The blue line is 10 degrees. Sorry. But yeah, this is the data graph analysis of distance versus ramp angle. Okay, so here is the t-test power or slide. So at the bottom you can see that we're comparing the 8-degree incline with the 10-degree incline group. At the top it says the two-tailed p-value equals 0.0022, and it says that this is very statistically significant. So pretty much what that means, the incline of the ramp is definitely impacting the distance that the car travels, because between these two like groups of data, they did not have a whole lot of overlap. So that means that the ramp's incline is doing something to the distance the car travels. And if you look at the bottom there, the mean, that is the average. So our average distance traveled for 8 degrees is 272.5 centimeters. And for 10 degrees, it is 307 centimeters. Our standard deviation, so I think that's like possible error, is 25, and then, or for the 8 degree incline, and then for the 10 degree incline, it is 17. So yeah, that is very statistically significant that these things aren't, like, or these two groups aren't really connected, but the ramp's incline does impact distance traveled by a car. Okay. Now let me go to the next slide. Okay, so I finally got the PowerPoint to work. Here is the second t-test. So now we're comparing group 8 and group 12. So again, this has a 0.001 two-tailed p-value. So again, this means that these groups don't really have a whole lot of overlap when it comes to the data points. So 8-degree incline doesn't allow for the car to travel as far as the distance as the 12-degree incline does. So at the bottom you can see that the mean of the 12-degree incline is 343, which is a lot higher than the average distance traveled by the 8-degree incline. So yeah, next slide. So here's the third t-test. Here we're comparing the 10-degree incline with the 12-degree incline. And at the top it says the p-value is 0.0034. So again, these data points are not overlapping a whole lot, so the incline of the ramp is definitely changing the distance traveled by the car. The bottom, for the average distance traveled by the 10-degree incline, it is 307 centimeters, while the 12-degree incline is 343 centimeters. So yeah, there's definitely a difference being made by this ramp's angle. Here are some possible sources of systematic and random error. So random error is like human error, kind of. So I think it's definitely possible that the precision of my measurements could be off a little bit, or it's definitely not like to the like absolute point. It was a little hard at sometimes to measure the distance that the car traveled because it wasn't like right next to the meter stick, so I kind of had to guess with my eye where it really was. Um, some systematic errors, so that's like something wrong with like the machinery I'm using or the experiment equipment I'm using. Some possible sources of systematic error could be the toy car hitting the meter stick when it traveled down the track. Because I noticed a lot of the time when I was releasing the car, it was going down the ramp just fine, but then once it got off the ramp, it started like hitting the meter sticks that I used to like create the track. And obviously, if it's hitting something like that, that's going to take away some of its speed and it's not going to travel as far. So I'd really like to conduct this experiment, maybe a different way, or like have a track enclosed a different way. So maybe I wouldn't run into this problem. We could get some more accurate data points and things like that. So in conclusion, I think my hypothesis was supported with the data I found. The inclination of the ramp is 100% a factor in the distance a car travels down a ramp. The steeper the incline of the ramp, the farther the distance the car will travel. And this is partially due to kinetic and potential energy, because the higher the incline of the ramp, the higher the position the toy car is going to have. So it's going to have more potential energy. And then more potential energy converts into more kinetic energy. So yeah, the 12-degree incline ramp definitely had the edge over the 8 and 10-degree angle. But yeah. Thank you. And here are some of my sources. Had a lot of fun doing this. Thank you. Bye-bye.